The universe has secrets older than time itself, imprints of its infancy hidden in the void. What if I told you the first moments after the Big Bang weren't fiery chaos, but a cosmic blank page? Scientists stare into the abyss, deciphering clues like detectives at a 13-billion-year-old crime scene. And here's the twist: the deeper we look, the stranger it gets. From galaxies that shouldn't exist to missing chunks of reality, the early universe defies every rule we know. Today, we're unraveling 30 of its most haunting mysteries, each one a thread in the tapestry of existence. Ready to see how much we've gotten wrong? The truth is written in the stars. If you know where to look, picture this: the universe as we know it springs into existence, but not from a dramatic explosion. In that critical first second, the rules of reality as we understand them simply break down. Here's the unsettling truth: even our most advanced physics hits a wall. The moment of creation is a blind spot, a cosmic secret locked behind what scientists call Planck time, an interval so short, it's a millionth of a billionth of a billionth of a billionth of a second. At this scale, gravity becomes a quantum force, warping space and time in ways Einstein's equations can't describe. Think of it like trying to read the first page of a book that's been ripped out. We can study the aftermath, but the opening lines gone. Some theories, like loop quantum gravity or string theory, attempt to fill this void, suggesting the universe might have bounced from a previous state or emerged from a higher dimensional ripple. But here's what keeps physicists up at night. Without understanding that first second, we might be missing the real story of how everything, from galaxies to the laws of physics, came to be. It's not just a gap in time, it's the missing key to existence itself. Now, let's shift our gaze to something even more elusive: black holes that shouldn't exist, at least not by today's cosmic rules. In the frantic first moments after the Big Bang, when space and time were still taking shape, the universe may have birthed trillions of tiny, primordial black holes. These aren't the colossal monsters we know today, formed from dying stars. No, these would be microscopic, some as small as an atom but packing the mass of a mountain. If they're real, they could be lurking everywhere, even right here in our solar system, invisible and undetectable for now. Here's where it gets stranger. Some scientists think these ancient relics might actually be dark matter, the mysterious substance holding galaxies together. Think about it, we've searched for decades, yet dark matter refuses to show itself. What if we've been looking in the wrong place? Primordial black holes fit the bill. They don't emit light, they barely interact with normal matter, and they could be everywhere. But if they exist, why haven't we caught one yet? Detecting something so tiny yet so dense is like trying to spot a single grain of sand in the ocean. Some experiments listen for the faint echoes of a black hole's death, a final burst of radiation called Hawking evaporation. Others scan for subtle distortions in starlight as these invisible objects drift through space. So far, silence, but the search isn't over. If we ever confirm their existence, it would rewrite cosmic history, proving that the infant universe played by rules far wilder than we ever imagined. The question isn't just whether they're real, it's how many are hiding in the dark, waiting to be found. One of the most startling leaps in cosmic history wasn't the Big Bang itself, it was what came immediately after. In less than the blink of an eye, the universe expanded faster than light itself, inflating from smaller than an atom to near cosmic scales. This wasn't just growth, it was a runaway explosion of space-time, smoothing wrinkles in the universe's fabric and setting the stage for everything to come. Yet the trigger behind this inflationary epoch, that's where the real puzzle begins. The leading suspect, a hypothetical energy field called the inflaton, a sort of cosmic domino that tipped the universe into hyperdrive. Picture pushing a ball uphill until it suddenly rolls down the other side, releasing stored energy in an unstoppable cascade. That's roughly how inflation might have begun, with the inflattened field's decay unleashing a torrent of expansion. But here's the catch: we've never detected this field. It's a ghost in the equations, indispensable yet invisible. Some theorists argue inflation wasn't a one-time event. If certain string theory models are correct, our universe might be one bubble in a foaming multiverse, where countless other inflations are happening right now unseen. Others propose even wilder ideas, like collisions between higher dimensional brains sparking our cosmic dawn. What's undeniable is inflation's fingerprints. Without it, the universe wouldn't be so eerily uniform, with galaxies spread just evenly enough for life to emerge. Yet the deeper we dig, the clearer it becomes. This wasn't just a quirk of physics. It was the universe's first and most critical decision, one we're still scrambling to understand. Early in the universe's story, an impossible escape happened, one that defies everything we know about symmetry. Matter and antimatter should have wiped each other out in a flash of energy, leaving behind nothing but empty space. So why do we exist at all? The fact that you're here right now, watching this, is evidence of a cosmic cheat, some tiny imbalance in the rules that let matter win. Scientists call this conundrum baryogenesis, and it's one of the deepest puzzles in physics. For every billion particles of antimatter in the early universe, there were 1,000,001 particles of matter. That razor-thin margin, just one extra particle in a billion, was all it took for stars, planets, and us to exist. But here's the catch: no known law of physics allows for that kind of favoritism. Enter CP violation, a glitch in the universe's mirror. Normally, matter and antimatter should behave like perfect reflections. Flip a particle's charge C, reverse its direction P, and it should obey the same law. But in rare cases, like with certain decaying particles called kaons and B mesons, the reflection cracks. The antimatter version behaves differently, breaking the symmetry we'd expect. Even with these clues, the math still doesn't add up. The amount of CP violation we've observed is 1,000,000 times too weak to explain the matter surplus. Some theories suggest undiscovered particles like neutrinos that flip their own identities could tip the scales further. Others propose that the imbalance didn't happen during particle collisions, but in the seething quantum foam of the universe's first moments. Whatever the answer, the stakes couldn't be higher. If matter and antimatter had played fair, the cosmos would be empty. That single, unexplained asymmetry isn't just a curiosity, it's the reason anything exists at all. And that means solving it isn't just about understanding the past. It's about rewriting the rules of reality itself. Deep in the cosmic tapestry, invisible threads weave through the void, magnetic fields stretching across galaxies, shaping the birth of stars and the fate of interstellar gas. But here's the catch: no one knows how they got there. The universe shouldn't have had magnets at birth. In those first fiery moments, matter was too hot and chaotic for magnetic fields to form. Yet today, they're everywhere, twisting through galaxy clusters, wrapping around black holes, even threading between stars. Somewhere between the Big Bang and the first galaxies, something flipped a cosmic switch, electrifying the void. Theories, there are a few. One suggests that tiny seed fields emerged from quantum fluctuations in the early plasma, like ripples in a pond but made of pure energy. Others propose that the violent churn of the first supermassive black holes acted like giant dynamos, spinning magnetic energy into existence. But here's the problem: simulations show these processes shouldn't have been strong enough to create the vast fields we see today. Then there's the real puzzle: their role in cosmic evolution. Without magnetic fields, galaxies might never have formed. They guide collapsing gas, fuel star formation, and even protect fledgling solar systems from deadly radiation. It's as if the universe needed these invisible forces to build anything at all. Yet their origin remains one of the quietest mysteries in cosmology. Unlike light or gravity, magnetism leaves no fossil record in the cosmic microwave background. To find answers, scientists now hunt for ancient galaxies with polarized light clues frozen in time. Because if we crack this mystery, we might finally understand why the universe didn't just expand but built. Somewhere in the cosmic dark, the universe's first true giants should still be shining, but we've never found them. These weren't just any stars. Born from pure hydrogen and helium in the universe's chaotic youth, population 3 stars were behemoths, hundreds of times more massive than our Sun. They lived fast, died violently, and forged the very first heavy elements that would later build planets and us. Yet despite decades of searching, not a single one has been spotted. Here's why their absence baffles scientists. According to every model of cosmic evolution, these stellar pioneers should have left traces either as faint survivors in distant galaxies or as chemical fingerprints in ancient gas clouds. Instead, we find only echoes. The oldest stars we've discovered, like Methuselah in the Milky Way, are actually population 2 already polluted with heavier elements from earlier generations. So where did the originals go? One theory suggests they self-destructed too completely. With no carbon or oxygen to regulate their nuclear furnaces, these stars might have burned so ferociously that they collapsed directly into black holes, leaving no stellar corpses behind. Others propose they were simply too bright for their own good. Their intense ultraviolet radiation may have torn apart neighboring star nurseries before new generations could form. The search isn't hopeless, though. New telescopes like the James Webb Space Telescope are scanning the deepest corners of space, hunting for the telltale glare of helium-only starlight. If found, these cosmic relics wouldn't just solve a mystery, they'd give us a front-row seat to the moment the universe learned how to shine. Until then, their absence remains a silent reminder. Sometimes the most important chapters of history are the ones that vanish without a trace. Imagine a universe where the stuff you can see, planets, stars, even your own hands, is just the faintest whisper of what's really out there. That's the reality we live in. Dark matter outweighs everything we know by 5 to 1, an invisible scaffold that holds galaxies together. But here's the twist: though it shaped the cosmos from the beginning, we still don't know what it actually is. In the early universe, dark matter did all the heavy lifting. While normal matter was too hot and chaotic to clump together, dark matter's gravity quietly sculpted the first cosmic structures, filaments of shadow stretching across the void. Without it, galaxies might never have formed. Yet despite its fingerprints being everywhere, dark matter refuses to show its face. Scientists have chased countless leads. The classic suspect: WIMP, weakly interacting massive particles. These hypothetical heavyweights would barely touch normal matter, slipping through our detectors like ghosts. Decades of experiments, from deep underground labs to space telescopes, have turned up empty. Then there are actions: ultra-light particles so tiny they behave more like waves than matter. Some theories suggest they could transform in magnetic fields, leaving faint traces we're only now learning to spot. But the plot thickens. What if dark matter isn't one thing but many? Some models propose an entire hidden sector of particles, each with strange new forces. Others wonder if we've misread gravity itself, that dark matter might be an illusion, a sign our equations are incomplete. The strangest part: this isn't just about filling a gap in physics. Dark matter's true nature could rewrite the story of how everything came to be. Until we crack this cosmic case, the universe's greatest architect remains a shadow, felt everywhere yet seen nowhere. Astronomers have long imagined the universe's first sunrise, that pivotal moment when darkness gave way to light and the cosmic dawn began. But pinning down exactly when those first stars flickered to life, that's where the story gets messy. Recent discoveries have thrown the timeline into chaos, with cutting-edge telescopes delivering contradictory answers. Take the James Webb Space Telescope, for instance, peering deeper into space and further back in time than any instrument before it. Webb has spotted galaxies so ancient they shouldn't exist. These fully formed cosmic cities appear barely 300 million years after the Big Bang, a blink of an eye in cosmic terms. According to most models, the universe simply didn't have enough time to build something so massive so soon. It's like finding a skyscraper in the middle of the Stone Age. Yet when we turn to radio telescopes listening for the faint echo of hydrogen from the early universe, they tell a different story. Observations of the so-called cosmic dark ages, a time before starlight, suggest the first stars ignited much later. The discrepancy between these two sets of data is staggering, leaving scientists scratching their heads. So who's right? One possibility is that star formation didn't happen uniformly. Maybe pockets of the universe ignited early, while others lingered in darkness far longer. Or perhaps our understanding of how galaxies form is fundamentally flawed, like trying to assemble a puzzle with half the pieces missing. What's undeniable is that the cosmic dawn wasn't a single event, but a staggered awakening across the cosmos. And as telescopes push further into the past, we're realizing just how little we truly know about those first moments of light. Every new observation doesn't just refine the timeline, it rewrites it. The dawn, it seems, was far stranger than we ever imagined. The cosmic scales don't add up, and that's putting it mildly. When the universe was a seething soup of particles just microseconds old, the number of protons and neutrons should have perfectly balanced their antimatter counterparts. Yet today, everything we see, planets, stars, even our own bodies, is made of matter. Where did all those extra baryons come from? This isn't just a rounding error in cosmic accounting. It's a violation so fundamental, it threatens to rewrite our understanding of creation itself. Rewind to the quark-gluon plasma, the universe's first state of matter. In this superheated chaos, particles collided and annihilated at blinding speeds. According to the math, matter and antimatter should have cancelled each other out completely. But Soviet physicist Andrei Sakharov uncovered 3 escape clauses, conditions that, if met, could tip the scales. First, the universe needed processes that didn't play by perfect symmetry. Second, it required moments where particles behaved differently than their antimatter twins. And third, these imbalances couldn't happen during equilibrium. They needed the frenzy of the universe's rapid expansion. Here's the catch: we've only found slivers of evidence for Sakharov's rules. Take CP violation, where certain particles decay slightly unevenly, or electroweak baryogenesis, where the Higgs field's shifting state might have briefly favored matter. But even combined, these effects are a million times too weak to explain the surplus we see. Some theories suggest more exotic culprits. Could primordial black holes have swallowed antimatter, skewing the balance? Might hidden particles like sterile neutrinos have tilted the cosmic seesaw? Or was there some fleeting asymmetry in the quark-gluon plasma itself, a microscopic bias frozen into reality before the first stars formed? Every proton in your body is a relic of this mystery. If even one of Sakharov's conditions had failed, the universe would be empty. Yet the how remains one of physics' greatest open cases, a puzzle written in the very particles that make us possible. There's something unsettling about the cosmic microwave background, the afterglow of the Big Bang itself. It should be random, a grainy snapshot of infant universe chaos. But when scientists mapped its subtle temperature variations, they found something that shouldn't be there, an eerie alignment with our own solar system. Dubbed the axis of evil, this pattern defies everything we thought we knew about cosmic symmetry. At first glance, the CMB looks like a celestial fingerprint, unique, irregular. Yet when researchers divided the sky, they noticed a peculiar trend. The largest fluctuations weren't scattered randomly. Instead, they seem to follow an invisible line, one that just happens to match the plane of our solar system. The odds of this happening by chance, less than 1 in 10,000. Skeptics call it a fluke, a trick of statistics. After all, humans are pattern-seeking creatures. Maybe we're seeing connections where none exist. But here's where it gets strange. Other independent observations keep reinforcing the anomaly. The alignment persists across different data sets like a cosmic conspiracy. Some theorists suggest it could be evidence of pre-Big Bang physics, relics of a previous universe imprinting itself on ours. Others whisper about undiscovered forces warping space-time on scales we can't yet measure. The real shocker, if the axis of evil isn't an illusion, it means the universe might have a preferred direction, a concept that shatters the bedrock principle of cosmology, that no place in space is special. Einstein's equations assume uniformity, but what if the cosmos has hidden seams, wrinkles we're only now glimpsing? For now, the debate rages. New telescopes are scanning deeper, searching for flaws in the data or signs of something stranger. Whatever the answer, one thing's clear: the universe might not be as indifferent to us as we once believed, and that's either the biggest coincidence in science or a clue that reality is far weirder than we ever imagined. The universe is expanding, that much we know, but how fast it's happening, that's where the math breaks down. For over a decade, astronomers have been locked in a cosmic tug of war over a single number: the Hubble constant, the rate at which space itself stretches. The problem: measurements from nearby galaxies don't match those taken from the afterglow of the Big Bang. The discrepancy is small, just a few percentage points, but in cosmology, even a tiny mismatch can signal a colossal misunderstanding. Here's the strangest part: when we measure expansion using pulsating stars and supernova in our cosmic neighborhood, we get one answer. But when we calculate it from the cosmic microwave background, the universe's baby picture, we get another. It's like checking your car's speedometer and GPS at the same time, only to find they're telling you different speeds. The implications far from trivial. If the discrepancy is real and not some hidden error in our methods, it could mean dark energy isn't constant as we assumed, but changing over time. Imagine a force that grows stronger or weaker as the universe ages, throwing off our predictions like a rogue variable in an otherwise perfect equation. Or perhaps there's an unknown particle, a relic from the early cosmos, subtly tweaking gravity on grand scales. Some theorists have even dared to suggest our entire framework for cosmology, the standard model that's held for decades, might need an overhaul. Could there be extra dimensions warping our measurements, or patches of the universe expanding at different rates? For now, the tension remains unresolved, a stubborn wrinkle in our cosmic map. What makes this mystery so urgent is its sheer reach. The Hubble constant isn't just about expansion, it's the yardstick we use to measure the age, size, and fate of the universe itself. Until we solve this puzzle, we're navigating the cosmos with two different compasses and no idea which one is lying. At the heart of almost every galaxy lurks a monster, a supermassive black hole weighing millions or even billions of times more than our Sun. But here's what keeps astronomers awake at night. Some of these giants existed when the universe was barely a toddler. How does something that massive form so quickly? The answer might rewrite everything we know about cosmic evolution. Take the quasar ULA's J1342, a beacon of light from just 690 million years after the Big Bang, powered by a black hole already 2 billion times the Sun's mass. That's like finding a fully grown blue whale in a toddler's swimming pool. By all known physics, such behemoths shouldn't have had time to grow. So how did they cheat the cosmic clock? One radical theory suggests they skipped the small stuff entirely. Imagine vast clouds of pristine gas collapsing directly into black holes without ever forming stars, a process called direct collapse. In the dense, metal-free environment of the early universe, these clouds could have rapidly crumbled under their own gravity, birthing black holes thousands of times heavier than the Sun from day one. No assembly required, but not everyone's convinced. Skeptics argue this process would need impossibly perfect conditions. No turbulence, no competing star formation, just a silent, catastrophic freefall. Enter an alternative, the merger theory. If countless small black holes formed from the first stars, they could have gorged on gas and collided relentlessly, snowballing into supermassive beasts faster than we ever imagined. Simulations show these chaotic feeding frenzies might have kick-started black hole growth at breakneck speeds. Yet both theories have gaping holes. Direct collapse lacks direct evidence, while the merger model struggles to explain how early black holes found enough fuel so quickly. There's even a wild card idea that primordial black holes from the universe's first second could have jump-started the process, lurking unseen until galaxies began to form. The truth, we're hunting ghosts in the cosmic dark. New telescopes like the James Webb are peering back to this critical era, searching for the faint glow of gas swirling into these primordial monsters. Because if we solve this riddle, we won't just understand black holes, we'll uncover the secret recipe for how galaxies themselves were born, and that changes everything. Imagine baking a cake where one ingredient stubbornly refuses to measure up, no matter how carefully you follow the recipe. That's exactly the dilemma cosmologists face with lithium in the early universe. According to the pristine math of Big Bang nucleosynthesis, the first 3 minutes of cosmic existence should have forged a specific cocktail of light elements: hydrogen, helium, and a solid dash of lithium. Yet when we peer back in time, the lithium levels are mysteriously low, 3 times scarcer than predicted. This isn't just a rounding error. Lithium's absence undermines one of our most trusted models of the universe's birth. One possible culprit: stars. Over billions of years, these cosmic furnaces might have consumed or transformed primordial lithium, leaving behind a deficit. Picture ancient stellar giants slurping up lithium like spaghetti, fusing it into heavier elements before it could accumulate. Observations of some old stars support this. Their lithium levels are suspiciously depleted, as if something erased the original supply. But here's where it gets thorny. Even the oldest stars we've found, relics from near the dawn of time, show this lithium shortfall. If stars are the thieves, they started stealing impossibly early. That's led some theorists to suspect more exotic explanations, like undiscovered particles altering nuclear reactions in the infant universe. Actions, those elusive dark matter candidates, could have subtly tweaked how protons and neutrons fused, skewing lithium production. Then there's the nuclear wildcard. What if our understanding of atomic physics itself is incomplete? Certain rare reactions between lithium and other particles, poorly studied in labs, might have destroyed the element faster than we realized. Alternatively, space itself could hold the answer. Primordial black holes or cosmic strings might have shredded lithium atoms in the universe's chaotic youth. The stakes are high. Lithium isn't just a cosmic curiosity, it's a benchmark for how we model the universe's first moments. Crack this puzzle, and we might uncover hidden laws of physics or realize we've been misreading the recipe all along. Staring at the cosmic microwave background is like looking at a perfectly mixed paint can: no streaks, no clumps, just eerie uniformity stretching across the sky. But here's the thing, it shouldn't be this smooth. In the universe's early days, regions now billions of light years apart were once too distant to exchange heat or information. So why does the temperature of the CMB vary by less than 1/1000th of a degree? It's as if hundreds of chefs in separate kitchens somehow baked identical cakes without ever speaking. Enter cosmic inflation, the leading explanation for this horizon problem. Picture the universe as a balloon inflating faster than light itself, stretching quantum fluctuations into cosmic scale uniformity in less than a trillionth of a second. Inflation doesn't just solve the smoothness puzzle, it predicts the subtle ripples we actually see in the CMB. Yet for all its elegance, inflation raises its own questions. What triggered this hyper-expansion, and why did it stop so abruptly? Not everyone's convinced inflation is the answer. Some theorists propose wilder ideas, like a speed of light that wasn't always constant. In these models, light in the early universe could have raced infinitely faster, allowing distant regions to thermalize before slowing down to today's speed limit. Others suggest the universe might have been born smaller than we think, with its edges mysteriously connected like a hall of mirrors. But here's the twist: each alternative comes with trade-offs. Variable light speed would require rewriting Einstein's relativity, while cosmic mirrors demand geometries we've never observed. Inflation, for all its unknowns, remains the simplest fix, but simplest doesn't always mean right. The deeper we dig, the clearer it becomes. The universe's smoothness isn't just a lucky break. It's a clue written in microwaves, hinting at physics we've yet to imagine. And until we crack it, we're left staring at that cosmic paint can, wondering who or what did the stirring. Somewhere in the cosmic equations, a phantom lurks: dark energy, the enigmatic force accelerating the universe's expansion. Today, it acts like a gentle nudge, barely noticeable, but rewind to the universe's first moments and things might have been radically different. What if dark energy wasn't always this quiet? What if it once roared? The phantom energy hypothesis dares to ask just that. Picture dark energy not as a steady presence, but as a wild, fluctuating force, one that could have spiked violently in the early cosmos. Some models suggest these phantom surges might have even triggered inflation, that hyper-fast expansion moments after the Big Bang. Think of it like a cosmic gas pedal suddenly slamming down, stretching space-time faster than light itself. Here's where it gets stranger. If dark energy's density once peaked in these phantom spikes, it could explain why the universe looks so finely tuned today. Those ancient bursts might have smoothed out wrinkles in space, set the stage for galaxies, then faded away, leaving only the faint, constant push we detect now. But there's a catch. Phantom energy defies conventional physics. It would require dark energy to have negative kinetic energy, a property so bizarre it could make the universe's expansion accelerate uncontrollably, eventually tearing apart atoms themselves in a big rip. Not all researchers buy into this radical idea. Skeptics argue it's a band-aid for gaps in our theories, an exotic solution in search of a problem. Yet others counter that the early universe was exotic, a place where normal rules didn't apply. If phantom energy left fingerprints, they might be hidden in subtle distortions of the cosmic microwave background, or in the way galaxies cluster across the void. Whether real or not, the phantom hypothesis forces us to confront a humbling truth. Dark energy's story might be far weirder than we ever imagined. And if it did shape the infant cosmos, we're not just decoding the past, we're glimpsing the universe's volatile, untamed youth. Among all the universe's elusive particles, neutrinos are the ultimate ghosts. Billions pass through your body every second without a trace. For decades, physicists assumed these nearly massless particles zip through space at the speed of light, obeying the Standard Model's pristine equations. Then reality threw a curveball. Experiments revealed something shocking. Neutrinos have mass, and not just any mass, a vanishingly tiny one, so slight it defies measurement. This discovery didn't just tweak the rules, it cracked the foundation of modern physics. The smoking gun came from neutrino oscillations. When scientists tracked these particles across vast distances, from nuclear reactors to underground detectors, they noticed something strange. Neutrinos morphed between three flavors: electron, muon, and tau. Here's the kicker: this shape-shifting act is only possible if neutrinos have mass. But how much mass? That's where things get messy. The heaviest neutrino is at least 6 million times lighter than an electron, placing them in a weight class all their own. Why does this rattle cosmology? Because the Standard Model, our playbook for particle physics, assumed neutrinos were massless. Their actual heft, however slight, throws off calculations about how the early universe evolved. Picture baking a cake where one ingredient's pinch more than the recipe calls for. Suddenly, the whole texture changes. Neutrinos, abundant as they are, would have subtly warped the formation of galaxies, the clustering of matter, even the echo of the Big Bang itself. Some theories scramble to patch the gap. Perhaps neutrinos gain mass by interacting with an undiscovered field, like the Higgs but stranger. Others propose their Majorana particles being their own antimatter twins, a property that could explain their feather-like nature. Then there's the wildest idea that neutrinos are cosmic immigrants arriving from extra dimensions we can't perceive. The implications ripple far beyond particle physics. If neutrinos really do tip the scales even slightly, they could be the hidden architects of dark matter, or proof that the standard model is just the first draft of a much weirder truth. One thing's certain, in the quietest particles, the loudest questions echo, and the answers might rewrite creation itself. The universe is woven together by invisible threads, a vast cosmic web of dark matter and gas stretching billions of light years. Supercomputer simulations paint a breathtaking picture, delicate filaments crisscrossing the void with galaxies strung along them like pearls on a necklace. But when astronomers peer into the real night sky, something's missing. Where are all the threads? This isn't just a slight mismatch. According to the latest simulations, the cosmic web should be dripping with faint, wispy strands, delicate tendrils of hydrogen gas linking galaxy clusters. Yet when we scan the heavens with powerful telescopes, those threads appear sparse, almost ghostly. It's as if someone snipped half the stitches from the fabric of space. So why the disconnect? One leading theory points to our own observational blind spots. These filaments are made of ultra-thin, ionized gas so faint they barely emit any light. Current telescopes might simply be overlooking them, like trying to spot spider silk from a mile away. New instruments, like the upcoming extremely large telescope, could change that with sensitivity sharp enough to detect these whisper-thin structures. But there's a darker possibility. What if the simulations themselves are wrong? The models rely on our best guesses about dark matter and galaxy formation, but those guesses could be flawed. Maybe dark matter clumps differently than we think, leaving fewer filaments behind. Or perhaps early black holes blasted apart these cosmic bridges before they could fully form. The stakes are higher than they seem. If the cosmic web really is patchier than simulations predict, it could mean our entire understanding of large-scale structure, how galaxies form and connect, is incomplete. And that would send theorists back to the drawing board to unravel why the universe isn't weaving its web the way we thought it should. For eons, the universe was a thick cosmic fog, a soupy darkness where light couldn't travel far without being swallowed by dense hydrogen gas. Then suddenly, a billion years after the Big Bang, the fog lifted. Space became transparent, as if someone had flipped a switch, but who or what flipped it? This is the reionization mystery, and it's one of the most pivotal unsolved chapters in cosmic history. Reionization didn't happen gently. The process was brutal, a celestial battleground where ultraviolet radiation tore electrons from hydrogen atoms, ripping apart the very fabric of the early cosmos. The question is, what produced that radiation? Two prime suspects emerge: quasars and galaxies, each with compelling evidence, yet neither fits perfectly. Quasars, the universe's ultimate powerhouses, seem like obvious culprits. These blazing cores of ancient galaxies, fueled by supermassive black holes, emit enough UV radiation to ionize entire swaths of space. But here's the catch: they're rare. Even at their peak, quasars were too few and far between to reionize the entire universe alone. It's like trying to light up a continent with a handful of flashlights. That leaves galaxies specifically, the first generations of stars. These weren't the tame, stable stars we know today. They were massive, hot, and brilliant, bathing their surroundings in a harsh glow of ionizing radiation. But there's a problem with this theory, too. Early galaxies were small and faint, and simulations struggle to show how their collective light could have pierced the cosmic fog so completely. The truth might lie somewhere in the middle. Perhaps it took both quasars igniting the process in dense regions, while galaxies finished the job, their combined radiation chiseling away at the darkness. Or maybe there's an undiscovered player, like exotic dark matter interactions or even population 3 stars, adding a wild card to the mix. One thing's certain, without reionization, the universe would still be opaque, and we'd never see the stars we take for granted. Solving this mystery isn't just about the past, it's about understanding the moment light truly broke free. And until we do, that billion-year transition remains one of cosmology's greatest untold stories. At the smallest scales, imaginable trillions of times tinier than an atom, the fabric of reality might not be smooth at all. Picture a bubbling, seething foam where space and time themselves churn unpredictably, popping in and out of existence. This is the quantum foam, a wild side of the universe where gravity and quantum mechanics collide, and our physics textbooks fall apart. Einstein's general relativity paints spacetime as a serene cosmic trampoline, bending gracefully under mass and energy. But down in the quantum foam, that elegant canvas dissolves into chaos. Here, virtual particles flicker into being, black holes form and evaporate instantly, and space-time itself becomes a turbulent storm. The problem: these two descriptions, relativity's smooth curves and quantum mechanics' frenzied fluctuations, refuse to play nice. It's like trying to merge a symphony with heavy metal, then wondering why the instruments keep breaking. The stakes couldn't be higher. If quantum foam is real, it means our understanding of reality is fundamentally incomplete. Some theories, like loop quantum gravity, suggest spacetime might actually be woven from discrete atoms of space, smoothing out the foam into something calculable. String theory takes a wilder approach, proposing extra dimensions where this foam settles into vibrating superstrings. But without direct evidence, these ideas remain mathematical daydreams. So how do we catch this foam in the act? One daring approach involves hunting for its fingerprints in starlight. As photons travel billions of years across the universe, quantum foam should subtly blur their paths like light passing through frosted glass. Telescopes like the Fermi Gamma Ray Space Telescope have scoured distant gamma-ray bursts for these telltale distortions, but so far, spacetime looks eerily smooth. Another tactic: listen closely. Gravitational wave detectors could one day pick up whispers of microscopic spacetime bubbles popping in the void. The truth might be even stranger. If quantum foam exists, it could mean reality itself is pixelated, a cosmic illusion rendered at the smallest possible scale. And that would rewrite not just how the universe began, but what it fundamentally is. Until then, the foam remains one of nature's most tantalizing maybes, a reminder that even empty space is anything but empty. Every magnet you've ever held has two poles, north and south, inseparable partners in the dance of magnetism. But buried in the equations of grand unified theories lies a phantom, the magnetic monopole, a particle carrying just one pole, north or south. These cosmic oddities should be everywhere, relics of the universe's searingly hot first moments. So where are they? The answer might trace back to inflation, that explosive expansion of the early cosmos. In simpler terms, monopoles were likely created in staggering numbers when the universe's forces first split apart. But then inflation kicked in, stretching space so rapidly that these particles were diluted to near nothingness, scattered so thinly they're now virtually impossible to find. It's like searching for a single grain of sand in an ocean that's grown 1 trillion times larger overnight. Not everyone's convinced the monopoles are gone, though. Some theories suggest they might still lurk in cosmic strings, defects in spacetime where conditions mimic the early universe's energy. Others propose they're hiding in plain sight, masquerading as heavy particles we haven't yet identified. Experiments like MOEDL at the Large Hadron Collider are hunting for them, watching for the telltale trails monopoles would leave as they plow through matter. Here's the twist: if we do find one, it wouldn't just solve a cosmic cold case. It could prove that the fundamental forces, electromagnetism, the strong and weak nuclear forces, were once united as a single superforce, a glimpse into the universe's most primal symmetry. Until then, the missing monopoles remain both a triumph for inflation's predictions and a nagging reminder of how much we've yet to discover. The cosmic microwave background is often called the universe's baby picture, a near-perfect snapshot of its fiery infancy. But zoom in close and you'll find something unsettling: mysterious cold spots, regions just a fraction of a degree cooler than their surroundings. At first glance, they might seem like cosmic static, random blips in the data. Yet these anomalies are too cold, too large, and too clustered to dismiss as mere noise. What carved these icy fingerprints into the fabric of the cosmos? One possibility is a cosmic defect, a glitch in space-time left over from the universe's hyperactive youth. Picture the early cosmos cooling rapidly, like metal hardening into a blade. If this process wasn't perfectly smooth, tiny cracks could have formed in reality itself, leaving behind textures called texture defects. These tangled knots of energy might have subtly warped the surrounding space, creating pockets of cooler radiation we now see as cold spots. Then there's the far wilder idea. These patches could be bruises from a collision with another universe. Some models of the multiverse suggest our cosmos isn't alone, that it's one bubble in an endless froth of universes. If another bubble bumped into ours during inflation, the impact might have left behind a cold imprint, like a shadow on the CMB. It's a radical notion, but not impossible, like finding a fingerprint on a window pane, evidence that something once pressed against our reality from the outside. But here's the catch: the cold spots might not be exotic at all. Critics argue they could simply be artifacts of how we process the data, or statistical flukes amplified by our human bias for patterns. After all, stare at any random noise long enough, and you'll start seeing shapes. The debate rages on, with new telescopes like the Simons Observatory scanning the sky for clues. If these cold spots are real, and not just cosmic illusions, they could be our first glimpse of physics beyond the Big Bang. Until then, they linger like spectral footprints, hinting at a history even stranger than we've dared to imagine. The James Webb Space Telescope was supposed to peel back the cosmic curtains, revealing the universe's first fledgling galaxies taking their baby steps. Instead, it found cosmic teenagers, fully mature galaxies strutting around when the cosmos was barely 5% of its current age. These galactic prodigies, massive and structured far sooner than any model predicted, are forcing scientists to ask, did we miss a chapter in the universe's playbook? One clue might lie in dark matter's hidden hand. In today's universe, dark matter acts like a slow, patient architect, gradually pulling gas into halos where galaxies can form. But what if the early universe played by different rules? Some theories suggest dark matter particles in the ancient cosmos might have collided more frequently, transferring energy in a way that turbocharged galaxy growth. Picture a cosmic construction crew working overtime. Dark matter's extra hustle could explain how galaxies assembled at breakneck speeds. Then there's the nuclear option. Maybe our laws of physics need an update. Certain tweaks to gravity, like modified Newtonian dynamics, could allow gas to collapse into stars faster in the early universe's dense environment. Others propose wilder ideas like phantom dark energy giving young galaxies an unnatural boost, or primordial black holes seeding galaxies like invisible scaffolding. But the simplest answer might be the most unsettling. What if we've misread the cosmic clock entirely? Distant light gets stretched as the universe expands, redshifting into infrared, the very wavelengths Webb excels at capturing. If our calculations for how much that light has shifted are even slightly off, these galaxies might not be as ancient as they seem. Yet early checks suggest the data holds firm, leaving us with a stark choice: rewrite the models or admit the early universe was far stranger than we ever dreamed. The phantom galaxies aren't just anomalies, they're cosmic rebellion, proof that the universe's childhood was anything but ordinary. And until we solve this puzzle, every new deep field image from Webb is a reminder: the deeper we look, the less we seem to know. At the edge of the observable universe, cosmic beacons blaze with the fury of 1 trillion suns, quasars, the brightest objects in existence, but their brilliance isn't the real puzzle. It's their age. These monsters, powered by black holes weighing billions of suns, flickered to life when the universe was barely a toddler. How does something that massive grow so fast? The answer might rewrite the rules of cosmic evolution. For a black hole to reach supermassive status, it needs to feast voraciously and continuously. But physics imposes a hard limit, the Eddington rate. Think of it as a cosmic speed limit for growth. Beyond this point, the radiation from infalling material pushes back so fiercely that it starves the black hole, like a fire so bright it blows itself out. To hit quasar-scale masses in just a few 100 million years, these early giants would have needed to break that limit, or cheat it entirely. One daring theory suggests they skipped the snack phase altogether. Imagine supermassive stars, hundreds of thousands of times heavier than our Sun, collapsing directly into black holes without the usual stellar fireworks. In the dense, metal-free environment of the early universe, such titans could have formed, died young, and left behind ready-made heavyweight seeds, no gradual growth required. Yet even this radical idea has cracks. Simulations show these stars would have been unstable, tearing themselves apart with intense radiation before collapsing neatly. That's led some researchers to propose an even wilder scenario: black hole mergers on an unimaginable scale. Picture cosmic demolition derbies where thousands of smaller black holes smash together in tight clusters, snowballing into quasars at record speed. But here's where observations twist the plot. Recent telescopic surveys have spotted quasars without the surrounding galaxy clusters needed to fuel such chaotic mergers. It's like finding a gourmet kitchen with no pantry. The truth might lie in a forgotten chapter of physics. Could dark matter's gravity have funneled gas directly into these early black holes, bypassing the Eddington limit? Or did the infant universe harbor exotic particles that supercharged accretion? Every new quasar discovery tightens the mystery, proving that when it comes to cosmic giants, the rules we know might just be the tip of the iceberg. Deep in the shadows of cosmic history, there's an invisible player that might have rewritten the universe's expansion: dark radiation. Unlike dark matter or dark energy, this mystery force isn't about gravity or acceleration. It's something far subtler: hypothetical particles streaming through space at near light speed, nudging the cosmos in ways we're only beginning to grasp. Picture the infant universe as a crowded dance floor. Photons and neutrinos zip around, shaping how matter clumps together. But hidden in the chaos, there could have been another guest: sterile neutrinos, a ghostly cousin of the neutrinos we know. These particles barely interact with anything, not even light, making them nearly impossible to detect. Yet their sheer energy might have tweaked the universe's expansion during those critical early moments, like an unseen hand tilting the scales. The clues, they're etched in the cosmic microwave background. Measurements of the CMB hint that something extra, some form of dark radiation, was at work, subtly altering how structures formed. But pinning down what exactly that was, that's where the challenge begins. Detecting something that barely touches normal matter is like trying to catch smoke with your bare hands. Scientists have scoured particle colliders, scanned underground detectors, even studied the skies for anomalies. So far, nothing definitive. Some theories suggest sterile neutrinos could decay into detectable particles, leaving faint trails in X-ray observations. Others propose they might distort the faint whispers of gravitational waves from the Big Bang. Yet even without proof, dark radiation's potential impact is staggering. If real, it could explain why certain measurements of the early universe's expansion don't quite match predictions. It might even hold the key to why neutrinos have mass, or how dark matter itself behaves. The hunt continues, armed with sharper telescopes and more sensitive detectors. Because if we ever spot this elusive player, It won't just solve a cosmic riddle, it'll reveal a whole new layer of reality hiding in plain sight. Imagine holding a map of the universe, except this map has no edges, no boundaries, and might loop back on itself like a cosmic game of Pac-Man. The shape of reality isn't just a philosophical question, it's written in the afterglow of the Big Bang. And the latest clues suggest the cosmos could be far stranger than we ever imagined. Astronomers have long assumed the universe is flat and infinite, stretching endlessly in all directions. But the cosmic microwave background tells a more nuanced story. Those subtle temperature fluctuations, the universe's first whisper, might hold the key to its true geometry. Some researchers argue the patterns align suspiciously well with a torus, a donut-shaped universe where traveling far enough in one direction would bring you back where you started. It's not science fiction, it's topology, the hidden mathematics of space itself. Here's what makes this idea so compelling. If the universe were finite but unbounded, like the surface of a balloon, large-scale SIMB patterns would repeat at specific intervals like echoes in a cosmic hallway. Recent analysis has spotted hints of these repeating swirls, though skeptics warn they could just be statistical noise. But a torus isn't the only contender. Other models propose a kaleidoscope universe where space folds into intricate Escher-like tiles. Some even suggest our entire cosmos could be the interior of a higher dimensional black hole, a hall of mirrors built into the fabric of reality. The real challenge testing these ideas. To prove the universe loops, we'd need to spot identical galaxy clusters or cosmic structures repeating across the sky, like finding your reflection in a funhouse mirror you didn't know was there. New surveys like ESA's Euclid mission are scanning deeper than ever, hunting for these ghostly duplicates. Whether finite or infinite, flat or folded, the universe's true shape isn't just about geometry. It's a window into the deepest laws of physics, and a reminder that reality might be far stranger than our textbooks dared to suggest. The cosmos thrums with a hidden symphony, ripples in space-time itself, left over from the universe's violent infancy. These primordial gravitational waves should be everywhere, the echoes of inflation's explosive crescendo. Yet when we listen, the universe gives us silence. Not the tranquil quiet of empty space, but an absence so stark it makes scientists question everything. Here's the puzzle: inflation. The universe's faster-than-light growth spurt should have generated a cacophony of gravitational waves, warping space-time like a drumhead struck by the Big Bang. Their fingerprints ought to linger in the cosmic microwave background, twisting the polarization of ancient light in telltale swirls called B-modes. But after decades of searching, from ground-based telescopes to space missions like Bicep and Planck, those swirls remain stubbornly missing. Two possibilities loom. Either inflation was far gentler than we thought, a whisper instead of a shout, or our instruments are still too crude to hear the universe's oldest music. The first option rattles theorists. A quieter inflation might mean exotic new physics, like modified gravity or an inflattened field with unexpected quirks. The second option, though, sparks a detective story. Hidden beneath the noise of interstellar dust and galactic magnetism, these waves could be too faint for current technology. Upcoming observatories like the Laser Interferometer Space Antenna LISA will scan lower frequencies, while next-gen CMB experiments hunt for subtler polarization patterns. But the stakes are cosmic. If we confirm the silence is real, it could mean inflation wasn't the solo act we imagined, but part of an ensemble with other forces shaping space-time in ways we've yet to dream. The quiet isn't just absence, it's a clue, and somewhere in that hush lies the answer to how reality first took shape. Somewhere in the cosmic void, galaxies are racing toward nothing, not the gentle drift of cosmic expansion, but a full-blown sprint, thousands of galaxy clusters hurtling in the same direction at speeds that defy logic. Astronomers call it the dark flow, and it's one of the most unsettling anomalies in modern cosmology. Either we're seeing a statistical mirage or the gravitational pull of something beyond our universe. The story begins with galaxy clusters, massive cities of stars moving en masse toward a patch of sky near the constellations Centaurus and Vela. At first, researchers dismissed it as a fluke. But as data piled up from multiple observatories, the pattern held. These clusters were being dragged somewhere at nearly 2 million miles per hour. That's not just fast, it's impossible under standard cosmology, where the universe's expansion should scatter matter evenly in all directions. So what's pulling them? One radical theory suggests the answer lies outside our cosmic bubble. If another universe exists beyond ours, separated by an unimaginable membrane of higher dimensional space, its gravity might be leaking through, tugging on our galaxy clusters like a magnet. Think of it as cosmic osmosis, a force so alien, it reshapes our reality from beyond the edges of space-time. Skeptics aren't convinced. They argue the dark flow could be an artifact of incomplete data or unseen biases in how we map galaxy motions. Others propose less exotic explanations, perhaps vast, undiscovered superclusters hidden behind the Milky Way's dust are skewing the measurements. But even these alternatives strain credibility, demanding structures far larger than anything our models predict. The debate isn't just academic. If the dark flow is real, it could mean our universe isn't the only one, that we're part of an infinite multiverse forever influenced by unseen neighbors. Future telescopes, like ESA's Euclid, aim to settle the question by mapping galaxy motions with unprecedented precision. Until then, the dark flow remains either the most tantalizing clue to a grander cosmos or the universe's most elaborate optical illusion. Either way, it's proof that even emptiness isn't as empty as it seems. The early universe should have been a churning, violent place, a turbulent sea of plasma where particles crashed together in endless chaos. Yet when scientists examine the cosmic microwave background, they find something unexpected. The primordial soup was eerily smooth. How does a boiling cosmic ocean suddenly turn glassy? This missing turbulence defies everything we know about fluid dynamics, and the answer might rewrite physics itself. Picture dropping a stone into a pond, ripples spread outward, colliding and swirling in complex patterns. At the universe's birth, the same thing should have happened on a cosmic scale. The Big Bang's explosive energy ought to have left behind a storm of ripples in space-time, a froth of turbulence frozen into the fabric of reality. But when we look, those ripples are suspiciously muted, as if some invisible hand smoothed them away. One clue lies in inflation, that lightning-fast expansion moments after the Big Bang. By stretching space faster than turbulence could form, inflation might have ironed out the chaos before it could take hold. Think of it like blowing up a balloon so quickly that any wrinkles vanish before they can settle. Yet even this explanation has gaps. Some simulations suggest turbulence should have left faint scars, subtle whirlpools in the cosmic microwave background that we've yet to detect. Another possibility, a cosmic damping mechanism we've never considered. Imagine an exotic particle, something beyond the standard model, that absorbed the turbulence's energy like a sponge, leaving the early universe unnervingly calm. Or perhaps dark matter played a role, its gravitational pull subtly steadying the primordial plasma. The wildest theories even suggest higher dimensions could have siphoned off the turbulence, dispersing it into realms we can't perceive. Whatever the truth, this puzzle isn't just about ancient physics. Turbulence shapes how galaxies form, how stars ignite, even how matter clusters into planets. If the early universe really was this smooth, it means our models of cosmic evolution might be missing a hidden force, one that tamed the chaos before it could shape the future. And until we find it, we're left staring into the cosmic deep, wondering what quieted the storm. Hidden in the math of black holes and quantum mechanics lies one of the most radical ideas in physics. What if our three-dimensional universe is just a projection, a cosmic hologram? The holographic principle suggests reality might encode all its information on a distant two-dimensional surface, like a movie etched onto film. But here's where it gets wild. Clues from the early universe hint this isn't just theory. It might be how creation actually works. Start with entropy, the measure of chaos in a system. Every black hole's event horizon has a maximum entropy it can contain, a limit discovered by Jacob Bekenstein and Stephen Hawking. Yet when you crunch the numbers, the infant universe's entropy was suspiciously low, as if it was respecting some invisible boundary. This cosmic thriftiness lines up eerily with holographic math, implying the early cosmos wasn't filling space, it was painting information onto its edges, pixel by pixel. Think of it like this: a glass can only hold so much water before it overflows. The universe, it seems, has its own glass, a fundamental limit on how much stuff it can contain. String theorists like Juan Maldacena took this further, showing how a higher dimensional universe could perfectly mirror a lower dimensional one, like a shadow cast by firelight. The equations work. The question is, does reality? Some physicists argue the cosmic microwave background holds the proof. If the early universe were truly holographic, its fluctuations should carry faint imprints, subtle statistical fingerprints of a 2D origin. Others hunt for evidence in quantum entanglement, where particles instantly influence each other across vast distances, as if connected by some hidden code. Of course, not everyone's convinced. Critics call it mathematical poetry, elegant but unproven. Yet if the holographic principle is real, it would mean the stars, galaxies, even your own thoughts, might just be data etched onto the fabric of spacetime itself. The universe wouldn't just have a boundary, it would be one, a cosmic illusion more profound than we ever dared to dream. What if the Big Bang wasn't the beginning, just the latest chapter in an endless cosmic cycle? Imagine a universe that collapses and rebounds like a celestial heartbeat, where every ending births a new beginning. This is the cyclic universe hypothesis, a radical reimagining of existence where the cosmos doesn't explode into being, it bounces back. At the heart of this idea lies quantum gravity, the elusive bridge between Einstein's relativity and the chaotic rules of the quantum world. In traditional models, gravity becomes infinitely strong during a collapse, crushing everything into a singularity, a dead end. But quantum gravity might rewrite that fate. Picture space itself as a stretchy fabric that can't tear. When squeezed beyond a certain point, quantum effects could create a repulsive force, turning collapse into rebound. It's not destruction, it's cosmic recycling, the allure. It solves some of the Big Bang's biggest puzzles. No need for a mysterious singularity to start everything. No arbitrary fine-tuning to explain the universe's perfect expansion rate. Instead, each cycle smooths and stretches spacetime, leaving behind echoes of past universes in the form of subtle patterns we might one day detect. Yet proving this isn't simple. A cyclic universe would erase most traces of its predecessors, like waves washing footprints from a shore. Some theorists hunt for faint imprints in the cosmic microwave background, twists or scars that inflationary models can't explain. Others suggest gravitational waves from the bounce might linger, hidden in the universe's hum. But so far, the evidence remains as ghostly as the idea itself. Skeptics argue the math is too speculative, the physics untested. Yet the cyclic universe persists, daring us to consider an even grander vision, that our cosmos isn't a one-time event, but a note in an infinite symphony of expansions and contractions. And if that's true, the question isn't just how our universe began, it's how many came before. As we reach the end of our cosmic journey, one thing becomes startlingly clear: the universe isn't just full of mysteries, it is a mystery. These 30 enigmas, from vanishing lithium to phantom galaxies, invisible threads to primordial black holes, aren't isolated riddles. They're pieces of a grand puzzle we're only just beginning to assemble. Every discovery doesn't just answer a question, it rewrites the questions themselves. Take the James Webb Space Telescope, peeling back layers of time to reveal galaxies that defy explanation. Or gravitational wave detectors, listening for whispers from the universe's first seconds. Each new tool brings us closer to solving these puzzles or stumbling upon even stranger ones. But here's the beauty of it. You don't need a telescope to join the adventure. Which mystery keeps you up at night? Is it the cosmic dawn's missing light, the ghostly pull of dark flow, or the holographic code that might underpin reality itself? Drop your theories in the comments, because the next breakthrough might not come from a lab, but from a spark of curiosity, a fresh perspective, a question no one thought to ask. The universe didn't reveal its secrets easily in the past, and it won't now. But that's what makes this story so thrilling. We're not just observers, we're detectives piecing together a cosmic case that's far from closed. So stay curious. The next chapter is being written, and who knows, the answer to one of these 30 mysteries might be just around the corner.